Very much. So I'll be giving you a brief overview of our product based on SPADs that were mentioned by the first speaker. We are a Swiss company based in Neuchâtel, and we are a fabless semiconductor focused on computational SPAD imagers. So we design and develop these circuits um, in order to facilitate entry into the SPAD detector market. So a brief overview of SPADs. So there's a special type of photodiode that operates above its breakdown voltage and has this three-step cycle that you see on the right. When the moment the photon hits the detector, we have a spike in the current that we need to quench to avoid damaging the device, and then we recharge the pixel to bring it back above excess bias. And this is a very fast cycle. It takes a few nanoseconds to go through, and we can run this continuously for these pixels. And the way we interface with them is by putting a very simple inverter after it and essentially transforming the SPAD into a digital device, because that pulse is directly converted into into the digital domain, which means there is no readout noise in these devices. We only have dark counts. And like I mentioned, this process is very, very fast. So we can count hundreds of millions of these events per second for each of these pixels, which gives us a very high dynamic range, because the noise floor is in the order of tens of counts per second, and then the top is hundreds of millions. And we do not saturate. These devices do not hit a ceiling, um, but they essentially keep counting. So if we have enough time and we integrate for enough time, we can extend this dynamic range, or we can extract the incident photon rate based on what we measure at the output. And an extra benefit is the picosecond jitter, the jitter beat from the moment the photon hits the diode, and the edge of the output pulse has a picoseconds of jitter, which allows us to use these pads for of time of flight, which is was the main driver for this technology, and is currently being used like this in commercial products, like the face recognition in Apple products, or laser distance measurement. And more recently, they've been used now in surveillance because of their single photon sensitivity. But in this case, we lose this single photon information from the pixel, and I'll get into more detail a little bit later. But the problem with these cameras and what's currently hindering their adoption is the data rates, right? Like I said, we're measuring millions of hundreds of millions of events per second per pixel, which results in a ridiculous amount of data. And this is an example of a detector that was published in 2017. So this was most likely the design like more than 10 years ago. And even at that time, it was producing 3 gigabytes per second if you were to run at full speed, which exceeds common interfaces and poses severe bottlenecks. So what's currently being done is either you operate these sensors in bursts of a few seconds, or you slow them down just to lower these data rates, or you sacrifice that single photon information. And by this, I mean, for example, you can count them on the device, and then instead of getting this photon hits, you get a photon counts over an integration period, which essentially turns it into a very sensitive camera, but you lose that timing precision of the photon. Apart from this, they're relatively complex. They were developed in academia. They're now scientific cameras, so they're designed for scalability or ease of integration into industrial products, and they have a higher cost compared to other alternatives because of these high performance electronic components that need to be integrated into them to support that very high data rate. So that's where we come into play with our computational SPAD sensor. So by computational, we mean that we've integrated pre-processing electronics into the same the sensor, right? And edge computing, if you want, where we process this raw data from the pixels directly on the device and extract that relevant information, thereby reducing the burden on the system, allowing it to be easier to integrate, reduce the power, because even now the majority of the power consumption from these cameras comes from the IOs that toggle at these very high data rates. And by pre-processing in parallel on the device, this allows us to have a significant increase in speed, in acquisition speed. So an example on our flagship product is our asynchronous detector. This is a 3000 pixel camera that has an event-driven output. So we've eliminated the raw output of the SPADs, and instead the camera only sends out photon hits. This allows us to be able to reconstruct the frame rate, if we wish, at up to 100 million frames per second, making it the fastest SPAD array of its kind. And it's all done over the USB 3 because of this high level of data compression. So if we were to look back at the plot I showed before, even at this small resolution of 3000 pixels, if we were to operate at full speed, we would be above uh, um, the data rates of even upcoming interfaces. However, by doing this pre-processing on the detector itself, we're reducing this by 2 orders of magnitude, and now we can operate it continuously with conventional, very easy to access interfaces. This also offers a path for miniaturization. You can see the camera in that picture. It's a 3 centimeter cube because there's no longer a need for this high performance electronics around it. Everything is on chip. The hard work is done on chip, and then externally we just control it as a normal detector. So what does an image captured at 100 million frames per second look like? Well, this is a 3D plot showing these live photon hits on the detector surface. You have the X, Y, and the time direction. You can see the photon hits as they arrive on the detector. And then if we were to slice and freeze one of these moments, we would get an image at 100 million frames per second, which is very underwhelming because at this very short exposures, right, the scene needs to be fairly strongly illuminated to be able to see something. So what we do is we can add these frames together to increase the exposure until we get an image that is that looks as we'd expect it to look. But then the question is, why do we need to operate at 100 million frames per second if in the end we're compressing it? Well, the answer is because there's a lot more information in these frames compared to the lower speed. Right? And an example here, 2 examples here actually, are of software-defined cameras. If we take this raw data captured at this very high frame rate, we can process it in software to emulate different types of cameras on the same data set. On the top here, you have an image of a scene where we have cars moving on the street. And of course, if you should all be familiar with taking a picture of a moving object, it becomes blurry. But if we simulate movement of the imager itself, then we can selectively focus on different objects in the scene based on their speed. Or in some other, if we use a more exotic shift of these binary frames, we can actually keep all of these objects in focus at the same time in the image. And on the bottom, you see an event information overlapped onto an intensity image, right? So an event camera combined with a normal imager on the same data set done live in with this data sets. So this is these are a few examples of what can be done by processing the streams of data. We've also demonstrated data compression algorithms or other camera modalities, and these were all run on one of our prototypes that has this the capability of running software, user-defined software directly on the behind the pixel, so no longer application specific like the previous array. Additionally, we also have smaller sensors. These are 1 or 2 pixel detectors that are designed for specific applications. The processing is specific to for example, performing correlations between individual pixels, or resolving the number of photons that lands on the detector. So no longer events, but more application focused or designed to interface with external hardware. And this is an example of such a device is a photon number resolver, where we have a cluster of SPADs that act as a single pixel, and then the digital circuitry on the chip uh, detects coincidences and outputs a pulse on a dedicated output if we have 1, 2, 3, 4, or more simultaneous photons that fall within a nanosecond window. And each of these pads can operate at 300 million events per second. That cycle is happening at 3 nanosecond periods. And on the bottom, you see an example where we've directly coupled this detector with a photon counter, like with a time tagger, so 4 channels simultaneously. And by counting these pulses, we can essentially see a hand diagram. We can see the Poissonian distribution of the photons as they land the detector while we adjust the laser intensity. And the curve that you see there is not fitted. It's actually just a direct plot of a Poissonian distribution that has the same average photon count as we measured, and it fits very well at the low light level. And then as we tailor off to the higher photon rates, because we're collapsing the bins, we see a slight deviation. But this is done without any comparators. There's no external circuitry. It's just counting pulses directly outputted by the chip. So the future is in fully customizable on-chip processing. I already mentioned some of the algorithms that we could run on our prototypes. And the direction we want to push SPAD imagers into is to have the ability to run custom code on the detector. And this gives extra benefits, right? We're further reducing the power consumption and making it easier to integrate into system. And ideally would want a detector that's just a plug and play replacement for other imagers, or where people develop their application or their system, they will no longer consider SPADs as being very difficult to handle. In case, just treat them as any other imager. And here in the picture, you have the prototype I mentioned, where we have an array of independent processors designed to directly interface with the SPAD pixels on top and process that data in a parallel fashion. So thank you very much for your time, and I'm open for questions.